How to draw chair conformations from cyclohexanes. Say we're given a molecule. It looks something like this. It's terrible drawing, but hopefully it's good enough. How do we draw the chair conformation? Well, firstly, let's start by actually drawing what the chair conformation should sort of resemble. Something like that. And I'm going to label starting here, up, down, up, down, up, down, and then at the other positions we're going to go down, so up, up, down, down, up. Notice that the ones up are straight vertical or down vertically, whereas the other ones are sort of angled upwards or downwards. So the red ones are going to be axial, whereas the blue ones are in the equatorial position. Now, the way I like to start is by determining our leaving group. In this case, also, I don't know why I drew a bromine here. This should just be a methyl. So, just pretend that instead of drawing that, I drew a CH3. Okay. Now, what I'll do is we find our leaving group, which is our bromine. You don't necessarily have to do it by the leaving group first. I just prefer doing it this way. And our leaving group, remember, the wedge is up and the dash is down. So our leaving group here, so bromine, up. It's attached to a hydrogen, so that's down. Let's go down this way. Well, there's a CH3, and that's up. So that's going to be equatorial. Attached to it is a hydrogen. It's not shown, but it's there. If we move to the next one, which is to here, it's a hydrogen on both. Moving to the next one, hydrogen on both again. Here, the dashed line, we have this R group, and that's down. So that means the up has to be a hydrogen. And the final one, this carbon here, well, that's going to be hydrogens on both. Now this is one of many different possible chair conformations that you could have done. We could have, instead, drawn something like this, where instead we could have done our bromine up on this side, and then we'd have our methyl here following the same exact step we did before. And we would get a conformation that looks like this. Both of these are viable. We could have also started with bromine up here, and then we could have continued in the same fashion. As long as you use the same process, you'll get a chair conformation that is completely valid. For a chair conformation, or for the molecule for it to be able to undergo an E2 mechanism, the leaving group must be in the axial position. Well, in both of these cases, the leaving group are in the axial positions, as you can see. And so both of these mechanisms can actually undergo an E2 reaction. If, for instance, we drew the chair conformation that looked something like this, I'll separate them. So if we had drawn a chair conformation where bromine is up, right? So if we drew it up here, and then this would be a hydrogen, and the next one would be a methyl that's up. This would be hydrogen, and then it's a hydrogen, 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 hydrogen. This is down, hydrogen. If we had drawn this chair conformation, we see that our leaving group is not axial. Therefore, this chair conformation cannot undergo an E2 mechanism. And so that would be how you draw your chair conformation.